Somewhere right now, a person is falling, maybe off a high diving board, maybe out of a plane with a parachute folded on their back. Maybe it's just a coin that slipped off the edge of a table. For the whole time they fall, before anything stops them, they feel no weight at all. Nothing presses on them. If a person falling held a ball out in front of their face and let go of it, the ball wouldn't drop away. It would hang right there, level with their eyes, falling alongside them at the exact same rate, keeping perfect pace. To someone falling, it looks for all the world like gravity has switched off. In the summer of 1907, a young clerk at the patent office in Bern, Switzerland, was sitting in his chair thinking about exactly this. His name was Albert Einstein. He was 28 years old. He had a steady government job, checking other people's inventions. And 2 years earlier, he had quietly turned physics upside down in his spare time. And now, a simple thought came to him. A man falling off a roof, he realized, would not feel his own weight while he fell. That was it. That was the whole thought. Einstein said later that it was the happiest thought of his life, and that it set him on the road to everything that came after. It sounds like nothing. A falling man feels weightless. Of course he does. But Einstein saw something underneath it that nobody had seen before. He saw that falling and floating are, deep down, the same thing. And if they're the same thing, then gravity is not quite what everyone had always assumed it was. Chasing that one idea took him 8 years, more than one wrong turn, and some of the hardest mathematics anyone had ever put to work. What came out the other end was a new picture of gravity, space, time, and the whole universe. It is called general relativity, and more than 100 years later, it is still standing, confirmed by test after test, and it has correctly predicted things so strange that Einstein himself doubted some of them were real. This is the whole story of that theory, from the ground up. It starts with that one thought about falling, the seed everything grew from. It goes back to pick up the earlier theory Einstein had to have first. It builds all the way up to the real equations in plain words, and follows Einstein through his own mistakes on the way to getting them right. Then it walks through the tests, the ones that have confirmed this theory for over a century, from a wobble in the orbit of Mercury to the satellites overhead that would fail without it. And it ends on the strangest children of the theory, black holes, spinning holes in space-time, the expanding universe, and ripples in space itself that took 100 years to finally catch. Start with the falling man, Einstein's happiest thought. For hundreds of years before Einstein, one fact about gravity had puzzled careful people, and it hides in plain sight. Drop a heavy rock and a light pebble from the same height at the same moment, they land together. The heavy one does not beat the light one to the ground. This seems obvious once it's said, and it's stranger than it sounds. The heavy rock is pulled toward the earth much harder than the pebble is. It weighs more, so why doesn't it fall faster? The answer is that the heavy rock is also much harder to get moving. It has more of what physicists call inertia, the stubbornness that every object has against being pushed around. The extra pull and the extra stubbornness cancel out perfectly, and everything falls at the same rate. Galileo worked this out around 400 years ago. He found that how fast a thing falls has nothing to do with how much of it there is. A cannonball and a musket ball dropped together, hit the ground together. 50 years after Galileo, Isaac Newton went at it a different way. He swung pendulums made of different materials, wood, metal, whatever he had, and timed their swings. They all kept the same time. From that he concluded that the two kinds of mass, the mass that responds to gravity and the mass that resists being pushed are really one and the same thing. Newton wrote gravity down as a force, an invisible pull reaching across empty space between any two lumps of matter, and his math was so good it ran the heavens for 200 years. But even Newton was bothered. He never could say what the pull actually was, or how it reached across all that empty space instantly, touching nothing in between. People kept checking that heavy and light things fall together, because it's the kind of fact that feels too clean to be an accident. Long before Galileo, a Flemish engineer named Simon Steven dropped lead balls of different weights off a church tower in Delft and listened for the sound of them hitting a wooden board below. One thud, not two. Much later, around 1908, a Hungarian named Laurent Eötvös built a beautifully sensitive instrument, a rod hung from a thin fiber with weights on each end, and used it to check whether different materials fall even the tiniest bit differently. They don't, down to about 1 part in a billion. Modern versions of the same test have pushed that another million times finer, and gravity still treats everything the same. And in 1971, an astronaut named David Scott stood on the airless surface of the moon, held out a hammer and a falcon feather, and dropped them together in front of a television camera. With no air to slow the feather, they hit the moon dust at the same instant. Newton saw all this as a happy accident of nature, a coincidence baked into his law with no reason behind it. Einstein, sitting in that chair in 1907, saw it as a giant clue. Here's the leap he made. Picture a windowless room, a sealed box with a person inside and no way to see out. Now suppose that box is sitting still on the surface of the earth. The person inside feels normal weight. Drop a ball and it falls to the floor, speeding up as it goes. Now take the same sealed box far out in deep space, away from every star and planet, and tie a rope to the top and haul it upward faster and faster, gaining speed at just the right rate. The person inside gets pressed to the floor exactly as if they had weight. Drop a ball, and the floor rushes up to meet it, so from inside it looks like the ball falls to the floor, speeding up as it goes, exactly as before. Einstein's claim was bold and simple. There is no experiment the person could do inside that sealed box to tell the two situations apart. Standing in gravity and being hauled through space by a rope are, as far as any measurement can say, the very same thing. Turn it around and the falling man comes right back. A person standing in a room on Earth feels gravity. A person in that same room, while the whole room falls freely, say the elevator cable has snapped and the whole car is dropping, feels nothing, weightless, floating, gravity apparently gone. And the person floating in a spaceship, coasting through deep space with the engines off, feels exactly that same nothing. Free fall in gravity and floating in empty space are the same. Standing in gravity and accelerating through empty space are the same. That is the equivalence principle, and it is the seed of the entire theory. Einstein had noticed that gravity and acceleration are two names for one thing. This wasn't just a nice thought to have. It came with a bill attached, and the bill was that some very strange things had to be true. In 1911, Einstein started cashing it in. If gravity is the same as acceleration, he reasoned, then two effects have to follow that nobody had ever measured. First, clocks deep in gravity have to run slower than clocks higher up. Time itself has to flow at different rates depending on where a clock sits in a gravitational field. Second, a ray of light passing near something heavy, like the sun, has to bend. Light has to fall, just like everything else. Both of these came straight out of the falling man. Both of them turned out to be true, and both of them are impossible to make sense of inside the older physics that everyone was using, because that older physics still treated time as the same everywhere, and light as traveling in dead straight lines. To see why the equivalence principle was so explosive, it helps to know the theory Einstein already had in his back pocket, the one he'd built 2 years before he ever thought about falling men. That theory is special relativity, and it had already broken time. Special relativity came out of a fight about light. For most of the 1800s, physicists thought light was a wave, and every wave they knew of traveled through something. Sound waves traveled through air, ocean waves traveled through water. So light, they figured, must travel through some invisible stuff that fills all of space. They called it the ether, and they pictured it as a still, motionless backdrop, the one thing in the universe that truly sat still, against which all real motion could be measured. In 1864, a Scottish physicist named James Clerk Maxwell wrote down the laws of electricity and magnetism, and out of his equations popped the speed. His math said light travels at one fixed speed, a bit over 186,000 miles every second, and that this speed does not depend on anything about the source. That was strange. Every other speed in the world depends on the point of view of whoever measures it. A ball thrown forward on a moving train goes faster over the ground than the same ball thrown on a still platform. But Maxwell's light didn't seem to care. So people went looking for the ether. If the Earth is flying through this still ether as it orbits the sun, then light should travel a little faster or slower, depending on whether it's going with that wind or across it, the way a swimmer is faster going downstream than across the current. In 1887, two Americans, Albert Michelson and Edward Morley, built an exquisitely careful instrument to catch that difference. They found nothing. Light came back at exactly the same speed in every direction, no matter how the Earth was moving. There was no ether wind. There was, as far as anyone could tell, no ether at all. Several clever people, including George Fitzgerald, Hendrik Lorentz, and Henry Poincaré, tried to patch the old picture by supposing that moving objects physically shrink in the direction they move by just the right amount to hide the effect. They got close to the answer, but they were still trying to save the ether. Einstein threw the ether out. On the 26th of September, 1905, he published a paper with the dull title of a paper about moving bodies and electricity, and in it he built the whole thing from two plain rules. First rule: the laws of physics are the same for everyone moving at a steady speed. There is no experiment anyone can run inside a smoothly moving train with the shades down that will reveal the train is moving at all. This idea was old, going back to Galileo watching things fall on a moving ship. Second rule, the one that broke everything: the speed of light is the same for every observer, no matter how they are moving or how the light's source is moving. Everybody who measures the speed of a light beam gets the same answer. The person on the platform and the person on the train racing toward the beam or away from it all get the same number. Those two rules sound harmless sitting next to each other. They are not. Hold them both at once and something has to give. And the thing that gives is time. Think about what speed even means. Speed is distance divided by time. If two people moving differently must both measure light at the same speed, but they cover different distances, then they cannot be sharing the same time and the same distances. Their clocks and their rulers have to disagree. That is exactly what Einstein found. Two moving observers cannot agree on how long a second lasts or how long a meter is, or even on whether two far apart events happened at the same moment. Take time first. A clock that moves fast runs slow. Seen from the frame, it races past. Not because the clock is broken. Time itself, for the moving thing, is passing more slowly. This is called time dilation, and at everyday speeds, it's far too tiny to notice, which is why nobody ever bumped into it before. But it is real, and we measure it constantly. High in the atmosphere, cosmic rays from space crash into the air and create tiny particles called muons. A muon lives only about 2 millionths of a second before it falls apart, and even at nearly the speed of light, that's not nearly long enough to reach the ground. Yet the ground is covered in muons. They reach us because they're moving so fast that their internal clocks are running slow from our point of view, and that slowdown stretches their brief lives just enough to complete the trip. Fast clocks run slow. The muons prove it every second of every day. Then there's length. A fast-moving object is shorter along its direction of travel. Measured from a frame, it's rushing past. A ruler flying by at near light speed is really squashed. And simultaneity, the idea that two things happened at the same time, falls apart completely. Two events that look simultaneous to one observer can happen in a clear order for another observer moving differently. And there's no fact of the matter about who's right, because there is no master clock in the universe. This is the piece Einstein was proudest of, and the piece that trips everyone up. Before him, everyone assumed time was a single river flowing at the same rate everywhere, the same now stretching across the whole universe. Einstein showed there is no universal now. Every object carries its own time, ticking at its own rate, and the rates only line up when things aren't moving much relative to each other. The most famous face of this is the twin story. Take two twins. One stays home on Earth, the other climbs into a ship and flies to a nearby star and back at just a sliver under the speed of light, over 99% of the top speed. To the traveling twin, the round trip takes about 2 years. She feels no strange effects the whole way, but when she lands and steps out, 200 years have passed on Earth. Everyone she knew is long dead. Her stay-at-home twin is gone, replaced by distant descendants. She has, in a real and physical way, traveled into the future. It sounds like a trick, but it is not. The two twins had different experiences. One of them turned around and came back, and when they compare notes, they agree completely on who aged less. Fast travel really does slow down time, and going fast enough for long enough means coming home to a world that has grown old in the meantime. One more thing fell out of those two little rules, and it's the most famous equation in the world, though we'll say it in words. Energy and mass are the same stuff. A tiny bit of mass is equal to a huge amount of energy, and the number that connects them is the speed of light multiplied by itself, which is enormous. This is why the sun shines and why a nuclear bomb is so violent. A small amount of matter is being turned into a titanic amount of energy. Einstein pulled that out of pure reasoning about light and motion in the same miracle year, 1905. So by 1906, Einstein had a gorgeous new theory. It joined space and time. It made light speed the fixed rock everything else bends around, and it was already being confirmed. But it had a hole in it, and Einstein knew it. Special relativity only works for observers moving at a steady speed in a straight line. The moment something speeds up, slows down, or turns, the neat picture gets complicated, and worse, the theory had nothing to say about gravity at all. Newton's old idea of gravity was an instant pull reaching across space with no delay, and that flatly contradicted Einstein's new rule that nothing, no signal, no influence can outrun light. The two theories couldn't both be right. Something had to give again. The word special in special relativity is there because the theory only covers a special, narrow case, steady motion with no gravity. Einstein wanted the general case. He wanted a theory that worked for accelerating, turning, falling observers, and that swallowed gravity whole. That's the theory the falling man opened the door to. And to walk through that door, Einstein needed to stop thinking of space and time as a stage things move on and start thinking of them as a single thing that can bend. That single thing has a name: space-time. The person who first saw it clearly wasn't Einstein. It was one of his old teachers, a mathematician named Hermann Minkowski, who had actually taught Einstein back in school and had once called him a lazy dog. In 1908, Minkowski gave a lecture that opened with a line people still remember. He said that from now on, space by itself and time by itself were doomed to fade away into mere shadows, and only a union of the two would keep any real standing. What he meant was this: special relativity had shown that different observers slice up space and time differently. One person's now is not another's. One person's foot-long ruler is another person's shorter ruler. But Minkowski noticed that gluing space and time together into one four-dimensional whole, instead of holding them apart as two separate things, makes the disagreements smooth out. The separate pieces shift around from observer to observer, but the combined thing stays put. Here is what four-dimensional means, plainly. To say where and when something happens takes four numbers. Three of them fix the place: how far east, how far north, how far up. The fourth fixes the time: when. A single point pinned down by all four, a specific place at a specific moment, is called an event. A firecracker going off, a hand clap, the exact spot and instant a raindrop hits the ground. Every event is a point in space-time, and any object, as it moves and ages, traces a continuous line of events through space-time, a path from each moment to the next. That path is called the object's world line. Every person has a world line. It starts where and when they were born and snakes forward through space-time, one moment at a time, for as long as they live. A rock sitting still has a world line, because even sitting still, it moves through time. Nothing sits out. Everything that exists is drawing a line through space-time right now. Now for the beautiful part, the thing that makes space-time more than a fancy way of speaking. In ordinary space, everyone agrees on the distance between 2 points. Two people with measuring tapes get the same answer for how far apart two nails are in a wall. In special relativity, that agreement broke. Moving observers disagree about distances, and they disagree about times. But Minkowski found a combination they all still agree on. Take the time between two events and the distance between them. Mix them together in a particular way, with the space part and the time part carrying opposite signs, and the result is a single number called the space-time interval. And this interval is the same for every observer, no matter how they're moving. It is the rock. Person A and person B disagree on how far apart two events were and how much time passed between them, but they agree exactly on the interval. Space and time separately are like shadows that stretch and shrink depending on where the light is. The interval is the solid object casting them. That minus sign, the fact that time enters the mix with the opposite sign from space, is the whole difference between space-time and ordinary space. It's why time feels different from a direction a person can walk. and it sorts every pair of events into three kinds. Some pairs are close enough in space and far enough apart in time that a slower than light signal could travel from one to the other. For those, everyone agrees which came first, and the earlier one could have caused the later one. Some pairs are so far apart in space and so close in time that not even light could get from one to the other. For those, there is no agreed order at all. Different observers see them in different sequences, and neither one can have caused the other. And right on the boundary between these two are the events a beam of light connects exactly. Draw this out, and it makes a shape called a light cone, spreading out from every event into the future and back into the past. The light cone is the edge of what any event can touch. Inside it, cause and effect. Outside it, no contact of any kind. Because everyone agrees on the interval, everyone agrees on the light cones, and so the whole universe agrees on what can cause what, even while it argues about clocks and rulers. Cause and effect survive, even after Einstein broke the universal now. Einstein, at first, didn't like Minkowski's version. He thought dressing his physics up in fancy geometry was needless showing off, extra learnedness that didn't add anything. He came around fast, because when he sat down to chase the falling man and build his general theory, Minkowski's geometry turned out to be the only language that could hold the idea. Flat spacetime, the smooth, even spacetime of special relativity, where all the light cones point the same way and world lines of free objects run straight, was the arena when there's no gravity around. But Einstein's whole insight from the falling man was that gravity is not a thing sitting inside that arena. Gravity is a bending of the arena itself. Put a heavy object into spacetime, and spacetime near it stops being flat. The light cones tilt, the straight lines curve, and things moving through that bent region get their paths bent too. And we, standing back and watching, call the bending gravity. Minkowski gave Einstein a flat sheet. Einstein's next 8 years were spent learning how to let the sheet curve and figuring out exactly how much it should curve around any given lump of matter. That turned out to be brutally hard. He got it wrong more than once, but the target was clear now. Space and time are one fabric. Matter bends the fabric, and the bending is gravity. That one sentence is general relativity in a nutshell, and it deserves a careful walkthrough, because every strange thing that comes later grows straight out of it. The core claim has two halves that feed each other. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. The relativist John Wheeler summed it up in a line physicists have loved ever since, and in plain words, it says the same thing. Stuff bends spacetime, and bent spacetime steers stuff. Those two sentences, running in a loop, are the whole show. A star curves the spacetime around it. The planets, moving through that curved region, get their paths bent into orbits. Their bending, in turn, is part of the total mass and energy that keeps the whole thing curved, round and round. The picture most people have seen for this is the bowling ball on a rubber sheet. Stretch a trampoline flat, roll a bowling ball into the middle, and it sinks down and makes a dip. Now roll a marble past it, and the marble curves toward the ball, maybe even circles it for a while before spiraling in. That's the standard cartoon of a planet orbiting a star, and it's a fine picture to keep, with two honest warnings stapled to it. The first warning is that the trampoline only works because there's real gravity underneath pulling the bowling ball down and making the dip. So in a way, the picture explains gravity by secretly using gravity, which is cheating. It's a memory aid, nothing more. The second warning is bigger. The trampoline only shows space bending. It leaves out time, and time is the more important half. Here is the part the cartoon hides. When space-time curves near a heavy object, it isn't mainly space that bends, it's time. Clocks run slower, closer to a mass, and faster farther away. A clock down at a person's feet runs very slightly slower than a clock up at their head because the feet are a hair closer to the center of the earth. And it turns out that objects, left alone, naturally drift toward wherever their own time runs slowest. That drift is what we feel as the pull of gravity. An apple falls off a branch because the ground below it sits in slightly slower time, and the apple's straightest possible path through space-time bends it toward that slower time. It doesn't feel a force, nothing yanks it. It's coasting freely along the natural path, and the path just happens to lead down, because the mass of the earth has warped the time around it. The apple falls for the same reason the falling man feels weightless. Both are simply moving the way free things move through curved spacetime. This flips the old idea of gravity on its head, completely. In Newton's world, an apple hanging on a branch is at rest, and the mysterious force reaches out and pulls it down. In Einstein's world, the apple sitting on the branch is the one being pushed, shoved upward by the branch, forced off its natural path, and the moment the stem snaps, the apple stops being pushed and finally moves naturally, falling freely, feeling nothing. The person standing on the ground reading this is not resting. The ground is pushing up on them every second, holding them off the straight path their body would rather take. That upward push from the floor is the only thing they actually feel. What everyone calls the downward pull of gravity is the shape of space-time, and the shape has no feeling to it at all. This is why an astronaut in orbit floats. They aren't beyond gravity, they're deep in it. They're just falling freely, following the natural path, feeling nothing. The same as the man off the roof, only they're moving sideways fast enough that they keep missing the earth and loop around it instead. None of this throws Newton away. That's important, and it's part of why the theory was believed. In ordinary conditions, weak gravity and slow speeds, Einstein's math folds right back down into Newton's old equations, almost exactly. Drop a ball, throw a baseball, fly a rocket to the moon, and Newton's numbers are still perfect for the job because the corrections general relativity adds are far too small to matter. Newton wasn't wrong. He was working in the weak corner where the fabric is nearly flat and the differences hide. Einstein's theory only pulls away from Newton's when gravity gets strong or speeds get huge near a dense star at the edge of a black hole across the whole universe. That's the deal any new theory has to honor. It has to explain everything the old one got right and then go further. And general relativity does exactly that. It also carries a deeper idea that Einstein cared about a lot, and it's the reason the theory is called general. Special relativity had said the laws of physics look the same to anyone moving at a steady speed. General relativity says the laws of physics look the same to absolutely everyone, including people who are accelerating, spinning, or falling. There is no special class of observers, no master frame, no fixed stage that the universe is glued to. Space-time is not a rigid backdrop that events play out against. It's a flexible thing that pushes and gets pushed, curving in response to what's in it and steering what's in it in return. Take all the matter and energy out, and what's left isn't empty space sitting there waiting. In this theory, the geometry itself is one of the actors. So the target Einstein was aiming at after 1907 was a single rule, a rule that would say precisely, exactly how much spacetime curves for a given amount of matter and energy. Get that rule right, and everything else follows. Orbits, falling apples, bending light, slowed clocks, all of it out of pure geometry. Get it wrong, even a little, and the whole thing collapses. Finding that rule is where the story gets hard, and where Einstein started making mistakes. The rule, when he finally got it, is a set of equations that carry his name. People call them the Einstein field equations, and they have a reputation as some of the deepest lines ever written down. They can be squeezed onto a coffee mug, but every symbol on that mug stands for a whole bundle of numbers. So what looks like one short line is really a tangle of 10 equations, all knotted together and all having to be true at once. No symbols here though, just what they say. They have two sides and an equal sign between them. That equal sign is the entire physics. It says the thing on the left equals the thing on the right, always, everywhere. On the left is geometry, the exact shape of space-time at a point, how much it's curved and in which ways. On the right is stuff, the matter and energy sitting at that point, and how it's moving and pushing. So the equation reads, in plain English, that the curving of spacetime right here is set by the matter and energy right here. Wherever there's more concentrated energy, spacetime curves harder. Wherever it's empty, spacetime relaxes toward flat. The geometry and the contents are locked together, point by point, across the whole universe. There's a good comparison close at hand. 50 years before Einstein, Maxwell had written equations that tie electric and magnetic fields to the charges and currents that make them. Tell Maxwell where the charges are and how they're moving, and his equations give back the fields everywhere. Einstein's equations do the same kind of job for gravity. Tell them how matter and energy are spread out and moving, and they give back the shape of space-time everywhere. And that shape, once it's known, tells everything else how to move. So the equations are a machine. Feed in the stuff, turn the crank, get out the geometry. Look a little closer at each side. The right side, the stuff side, is more than just how much mass is sitting there. It's a full accounting of energy in all its forms, because energy and mass are the same thing, so energy curves space-time too. Light curves space-time, heat curves space-time a tiny bit, and it's not only the amount, it's the motion, the momentum, and even the pressure and the internal push and pull inside the material. All of that goes into the ledger on the right. This has a startling result. A sealed box of hot gas weighs a hair more than the same box cold, because the extra heat energy adds to the gravity. Pressure itself gravitates. Everything that carries energy bends spacetime, and the right side of the equation is the complete list of everything that's there. The left side, the geometry side, is built out of one central object, the thing physicists call the metric. The metric is the local rulebook for measuring spacetime. At every single point, it sets how to measure distances and how to measure time and how the two blend together right there. In flat, empty spacetime, the rulebook is the same everywhere, plain and boring. Near a mass, the rulebook changes from place to place, and that changing rulebook is exactly what curvature is. Solving Einstein's equations means solving for the metric. Get the metric, and the shape of spacetime is known everywhere, and from the shape comes every orbit, every falling path, every bent light ray, every ticking clock. The whole behavior of gravity in some situation is hiding inside that one rulebook, waiting to be read out. Now, the feature that makes these equations both beautiful and monstrous: they are non-linear. That's a plain idea underneath a fancy word. Maxwell's equations for electricity are linear, which means two problems can be solved separately, and their answers added together to get the result for both at once. Light beams pass right through each other without tangling. Because of this, Einstein's equations don't work that way. The two can't be solved separately and added. The reason is deep and a little dizzying. Gravity itself carries energy, and energy, as the right side told us, curves space-time. So gravity makes gravity. A region of curved space-time has energy in the very curving, and that energy curves space-time some more, which adds energy, which curves it more. The equation feeds back into itself. This is why gravity, unlike the other forces, is such a nightmare to calculate. Every source of gravity is also fed by its own gravity, all the way down. Two black holes drawing together aren't a simple sum of two black holes. They're a churning, self-feeding storm, and the only way to work out what happens is to hand the equations to a powerful computer and let it grind through the whole tangled mess, step by step. Woven into the equations, without Einstein having to add it by hand, is the law that energy and momentum can't just vanish or appear from nothing. The very form of the equations guarantees it. That was one of Einstein's hardest tests while he was searching, and the version that broke that law was a version he had to throw out. And at the far end, where gravity is weak and things move slowly, the equations become Newton's old law of gravity again. The same falling apples, the same orbits, the same numbers people had trusted for 200 years. Newton lives inside Einstein as the easy special case. Because the equations are so tangled, solving them exactly is close to impossible, except in very tidy, very symmetric situations. A single round object all by itself, a perfectly smooth universe. Einstein himself assumed nobody would ever find an exact solution and worked only with rough approximations. He was wrong about that, and he found out he was wrong within a couple of months. From a soldier writing letters from a war. That's coming. But first, there's one more piece of the machinery to understand. Because the equations only tell space-time how to curve. They don't, by themselves, tell a planet how to move once the curving is done. For that, there's a second, simpler rule, and it's the exact rule that turns geometry back into gravity. The rule is this: an object that has no forces on it, nothing pushing or pulling, no rocket, no rope, no friction, moves in the straightest possible line through space-time. That's it. It goes as straight as the shape of space-time allows. The name for the straightest possible line through a curved space is a geodesic, and once geodesics make sense, gravity stops being a force and becomes plain geometry. Start on the ground with something everyone has seen. Take a globe, a model of the Earth. What's the shortest, straightest path between two cities, say one in North America and one in Europe? On a flat map, it looks like a straight line drawn more or less due east. But that's not the real shortest path, and pilots know it. The real straightest path arcs up toward the north, over Greenland maybe, and back down. That arc is called a great circle, and it is the geodesic, the straightest line there is on the curved surface of a sphere. It looks bent on the flat map only because the map lies about the curvature. On the actual round Earth, it's dead straight, the path traced by never turning the wheel. This is the whole idea in miniature. On a curved surface, the straightest possible lines don't look straight to someone expecting flat world geometry. They curve, and they curve because the surface curves, not because anything is pushing them. Now here's the second piece, and it's the one that turns geodesics into gravity. Imagine two people standing a few feet apart on the equator, both told to walk due north, perfectly straight, never turning. They set off on parallel lines, but as they walk, without either of them ever steering. They slowly drift toward each other. By the time they reach the North Pole, they bump into each other. Neither one turned, neither one felt a force. They walked as straight as they possibly could, and still they came together, because on a curved surface, straight lines that start out parallel don't stay parallel. If one of those walkers didn't know the ground was curved, they might swear some mysterious force was pulling them together. There is no such force. There's only the shape of the ground doing the work. That drifting together of straight paths is what curvature looks like from the inside. Gravity is exactly that. One dimension up. Drop two balls side by side from a great height. As they fall, they both head for the center of the earth, so their paths, like the two walkers heading for the pole, slowly lean toward each other. Watched closely enough, the two falling balls drift together as they drop. Nothing reaches across the gap to pull them. They're both simply following the straightest paths they can through a space-time that's curved around the earth, and those straight paths lean into each other on their own. This is the honest heart of the whole theory. Gravity is the coming together of naturally straight paths in curved space-time. Nothing reaches out, nothing pulls. Things just go straight, and straight has been bent by the mass nearby. One thing needs adding, because it's easy to miss. When a ball falls, it isn't just moving through space, it's moving through space-time, and it's mostly moving through time, forward into the future, the way everything does. Even a ball that looks like it's sitting still is barreling through space-time because it's aging, second after second. So its world line, its path through space-time, is nearly all time and only a little space. When the mass of the earth curves the time around it, making time run slower down low, that great forward march through time gets tilted, ever so slightly, toward the slower time region below. Over the fraction of a second the ball is in the air. That tiny tilt is enough to send it to the floor. This is why gravity feels so strong, even though the Earth barely dents space-time at all. The dent is tiny, but everything is racing through time so fast that even a tiny tilt in that huge forward motion adds up to a hard fall. The apple drops fast because it's moving through time at the speed all things move through time, which is enormous, and the mass of the Earth has bent that motion downward. A planet's orbit is the same story, dressed up. The Earth going around the sun is not being lassoed by an invisible rope. The Earth is going straight, the straightest path it can, through the space-time the sun has curved. That straight path, flattened back down and seen as just the space part, comes out as a loop, an orbit, year after year. Take the sun away and space-time near the Earth would go flat. The straightest path would become a genuine straight line, and the Earth would sail off into the dark in a straight shot. The orbit exists purely because the sun keeps the space-time curved, and the Earth keeps faithfully going as straight as that curved space-time permits. Kepler and Newton could describe that orbit with beautiful accuracy. Einstein explained why it's there. It's a straight line that only looks like a loop because we can't see the curve of the thing it's drawn on. So the two rules of general relativity fit together like a hand in a glove. Matter and energy curve space-time, and that's the field equations. Objects with nothing pushing them follow the straightest path through that curved space-time, and that's the geodesic rule. Put the two together, and there's a complete engine for gravity. No forces anywhere, just geometry and motion. Sun bends space-time. Earth goes straight through the bend. We call the result an orbit. Earth bends space-time. Apple goes straight through the bend. We call the result a fall. Everything Newton attributed to a pulling force, Einstein got from shape. And here's the quiet triumph in it. The apple and the moon and a beam of starlight all follow the same rule, the straightest path through whatever space-time they're in, with no regard for what they're made of. The universality that puzzled Galileo and Newton, the fact that everything falls the same, isn't a coincidence anymore. It's built in from the start, because the path doesn't depend on the object at all. It depends only on the shape of space-time, and the shape is the same for everyone passing through. That's the finished theory, at least in its bones. It took Einstein 8 years to build it, and the building was not smooth. The clean story just told, matter curves space-time, things go straight through the curve, took him down several wrong roads first. Those wrong roads matter because they show that even the sharpest mind of the age got the details wrong over and over before the pieces finally clicked. The whole thing took Einstein 8 years, from the falling man in 1907 to the final equations in late 1915. That's a long time to chew on one problem, and he wasn't chewing slowly. He was working hard, publishing along the way, and getting it wrong in public. Right after the happiest thought, in a paper from around 1907 and 1908, he laid out the equivalence principle and drew his first real prediction from it, that clocks should run at different rates depending on where they sit in gravity. Time dilation from gravity, called years before anyone could measure it. So far so good. Then, in 1911, came the accelerating box and a sharper set of predictions. He worked out that a clock at the top of a box being hauled upward through space runs faster than a clock at the bottom, and by the equivalence principle, the same has to be true in gravity. Top clocks fast, bottom clocks slow. And he predicted that light passing the sun would bend, and he even put a number on it. The number was about 8/10 of 1 arcsecond, an arcsecond being a sliver of an angle, roughly 1/3600th of a single degree. Here's the thing, that number was wrong. It was too small by a factor of 2. Einstein had used a rough approximation that didn't fully account for the curving of space, only the slowing of time, so he got half the real bending. He didn't know it was wrong yet. He was urging astronomers to go photograph an eclipse and check it. As it happened, the expeditions that tried in those years got rained out, clouded over, or caught by the outbreak of war, and none of them got a clean measurement. That failure was a lucky break for Einstein. If anyone had gotten a good photograph then, they'd have proven his 1911 number wrong, and the whole theory might have been dismissed before it was even finished. He fixed the number in 1915, and the corrected value was about 1 3/4 of an arcsecond, twice the old figure. That's the number that would later be tested. Somewhere in here, Einstein worked through another thought experiment that pushed him over a crucial line. He imagined a spinning disk, a merry-go-round, and thought carefully about measuring it while it turned. He realized that because of the length contraction from special relativity, a ruler laid around the spinning rim would be squished, while a ruler along the radius would not. So the ratio of the way around to the way across would come out different from what flat geometry says it should be. Plane geometry was failing on the spinning disk, and that told Einstein something enormous. If acceleration is the same as gravity, and acceleration bends geometry like this, then gravity must bend geometry too. Space-time, in the presence of gravity, cannot be flat, it has to be curved. This is the moment the vague idea of curvature became a hard requirement, and it left Einstein with a problem, because he did not know the mathematics of curved spaces. He was a physicist, not a geometer. So, in 1912, Back at his old school in Zurich, he went to a friend, a mathematician named Marcel Grossman, and more or less begged for help. Grossman pointed him at a branch of mathematics most physicists had never touched, the geometry of curved spaces worked out decades earlier by Bernhard Riemann, and the tools for handling it built by Italian mathematicians. This was the language Einstein needed, the machinery for describing curvature precisely, in any number of dimensions, without picking any special point of view. He and Grossman published a first attempt together in 1913, and then Einstein promptly talked himself into a serious mistake. He convinced himself, through a clever-sounding argument, that the equations could not have the full freedom he wanted, the freedom to look the same to every observer, no matter how they moved. His argument, later called the whole argument, seemed to show that such fully free equations would give nonsense, two different futures from the same starting point. So he backed away from exactly the principle that turned out to be right. For most of 1914 and into 1915, he chased a more limited set of equations that didn't have that freedom, and he kept running into walls. The limited equations didn't work either. They came out inconsistent. By late 1915, he was worn down and worried, and there was a real chance someone would beat him to it, because the great mathematician David Hilbert was working on the same problem from the mathematical side. So Einstein went back and looked hard at the whole argument that had scared him off, and he found the flaw in it. His own reasoning had been wrong. The full freedom was allowed after all. With that, the dam broke, and in November of 1915, he wrote a burst of papers in quick succession, week after week, closing in on the answer. He almost fumbled it at the finish. The equations he published in October of 1915, right before the final ones, were still not quite right. They looked clean, and they even predicted the wobble in Mercury's orbit correctly, which thrilled him, but they had a fatal flaw. They only stayed consistent if the whole universe had the same density everywhere, if air and rock and even empty vacuum all had the identical amount of stuff packed into them, which is plainly false. That broke the sacred law that energy can't come from nowhere. So he fixed it. On the 25th of November, 1915, he presented the final version to the Prussian Academy of Sciences in Berlin, a corrected set of equations with one extra piece added on the geometry side that made everything balance. Those are the equations that survive today. The right rule at last, after 8 years and a string of wrong ones. David Hilbert had arrived at essentially the same equations, at almost the same moment, from an elegant piece of pure mathematics, and historians have argued for a century about who had exactly what on exactly which day. Hilbert himself never claimed the theory. It was Einstein's physics, Einstein's 8-year climb, Einstein's idea from the falling man, and the world has always called it Einstein's theory. There's a story about how forbidding it all seemed at the time, and it's probably too good to be exactly true, but people told it anyway. A physicist supposedly said to Arthur Eddington, one of the few who grasped the theory early, that he must be one of only 3 people in the world who understood general relativity. Eddington went quiet, pressed not to be modest. He said he was just trying to think who the third person might be. Only 3 people in the world. That was the reputation. And yet within a few years, this fearsomely difficult theory was going to be dragged out of the equations and checked against the actual sky, and it was going to pass. A theory is only as good as the tests it survives, and general relativity was about to start surviving them. Einstein himself set the terms, and they were harsh. He said the beauty of the theory was that it stood or fell as a whole. If even one thing it predicted turned out wrong. The whole structure had to be thrown away, because there was no way to patch it without wrecking it. That's a dangerous way to build a theory. It gives reality 100 chances to kill it. General relativity has taken those chances for over a century now, and it's still standing. Here's how the checking started. The first win came from a planet that had been misbehaving for over 50 years. Mercury, the closest planet to the Sun, does not quite orbit the way Newton says it should. Under Newton's gravity, a lone planet circles the Sun in a fixed ellipse, tracing the same oval forever, with its closest point to the Sun always in the same place. Real planets aren't alone, so they tug on each other, and those tugs make each planet's ellipse slowly rotate over time, the whole oval turning a little each century. For Mercury, astronomers carefully added up every tug from every other planet and worked out how fast its orbit should turn. Then they measured how fast it actually turns. The two numbers didn't match. There was a leftover, small but stubborn, about 43 arcseconds per century, a rotation of the orbit that nothing in Newton's universe could explain. An arcsecond, remember, is a tiny sliver of angle, so 43 of them per 100 years is a whisper. But it was real, and it wouldn't go away. A French astronomer named Urbain Le Verrier had spotted the problem back in 1859. He had a guess, and it was a reasonable one. Years earlier, he'd predicted the existence of the planet Neptune by noticing that Uranus was being tugged by something unseen, and Neptune was found right where he said it would be. So he tried the same trick on Mercury. He proposed another hidden planet, one even closer to the Sun, whose gravity was nudging Mercury's orbit. He even gave it a name, Vulcan. Astronomers searched for Vulcan for decades. They looked during eclipses. They looked at the Sun's face for a dark dot crossing it. They never found it. There is no planet Vulcan. The leftover in Mercury's orbit just sat there, unexplained. A small crack in Newton's 200-year-old theory. When Einstein finished general relativity in 1915, he ran the numbers for Mercury, and the theory, with no adjusting, no hidden planet, no fudge factors of any kind, coughed up the missing 43 arcseconds per century exactly. It came straight out of the geometry. Near the Sun, space-time is curved enough that Mercury's orbit doesn't quite close up on itself each time around. The ellipse creeps forward a hair every orbit, and over a century it adds up to precisely the amount that had been missing. Mercury, being closest to the Sun, sits in the most curved space-time of any planet, so it shows the effect most. Einstein said later that when he saw the numbers match, he was so excited he couldn't work for days, and that he felt something snap inside him. He wrote to a friend that his wildest dreams had come true. He hadn't set out to explain Mercury. The explanation just fell out of the equations, unbidden, correct. That's the kind of thing that makes physicists believe. Explaining Mercury was powerful, but it had a weakness as evidence. The 43 arcseconds were already known before the theory arrived, so a skeptic could grumble that Einstein had tuned his theory to fit an answer he already had. He hadn't, but the grumble was possible. What the theory really needed was a fresh prediction, something nobody had measured yet, a number Einstein could write down in advance and then have the universe checked against it. He had one ready: light bending. If gravity curves space-time, then light passing near a heavy object has to follow the curve and bend. Einstein predicted that a ray of starlight, just grazing the edge of the Sun, would be deflected by about 1 3/4 of an arcsecond, twice what the old half-baked Newtonian guess gave. The trouble is The stars right next to the sun normally can't be seen because the sun's glare drowns them out. There's exactly one time they can, during a total solar eclipse, when the moon blocks the sun's face and the sky goes dark enough that nearby stars pop out. So the test was this: photograph the patch of sky right around the sun during an eclipse, measure exactly where those stars appear, then photograph the same patch of sky months later at night when the sun is elsewhere, and see if the stars shifted. If Einstein was right, the stars near the sun's edge would look nudged outward, away from the sun, by that tiny predicted angle, because the sun's gravity had bent their light on the way to Earth. An English astronomer named Arthur Eddington took up the challenge. There was an eclipse coming on the 29th of May, 1919, and Eddington organized two expeditions to catch it, one to the town of Sobral in northern Brazil, and one to the island of Principe off the west coast of Africa. Getting there, hauling delicate telescopes across the world, waiting out clouds, it was a real ordeal, and the war had just ended, but they got their photographs. They measured the star positions, and the stars near the sun were shifted outward by close to the amount Einstein had predicted, and clearly more than the old Newtonian value. Eddington announced that Einstein was right. The news went around the world and landed on the front page of newspapers everywhere. Overnight, an obscure German physics professor became the most famous scientist alive, the man who had corrected Newton. Somebody asked Einstein what he'd have done if the eclipse measurements had gone against him. He said he'd have felt sorry for God because the theory was correct regardless. He wasn't really joking. He trusted the equations more than he trusted any single measurement. And it's a good thing the deeper trust was there, because that first eclipse measurement was shakier than the headline suggested. Eddington had only a handful of stars to work with. The instruments were finicky, the error bars were embarrassingly large, and critics have argued ever since about whether he leaned on the data to get the answer he wanted. Modern reanalysis of his actual photographs suggests his conclusion was sound after all. But the honest truth is that the 1919 result, taken alone, didn't prove much. What settled it was doing it again and again and again. In 1922, a team from the Lick Observatory measured a different eclipse from a remote station in Australia, with hundreds of stars this time instead of a handful, and got the same answer. It was checked again in the 1950s and again in the 1970s. And then radio astronomers, who can measure the bending of radio waves from distant quasars as the sun passes in front of them without needing an eclipse at all, pinned the number down with beautiful precision. Light bends by exactly the amount Einstein said. The shaky first measurement turned out to be pointing the right way, and everything since has confirmed it. There was a third classic test, and it took longer to nail down. Einstein predicted that light climbing up out of gravity, moving away from a heavy object, would lose a little energy and get slightly redder. Its color shifted toward the red end. This is the gravitational redshift, and it's the flip side of clocks running slow in gravity. It's a small effect and hard to catch. It was first looked for in the light from white dwarf stars, which are incredibly dense and have strong gravity, and it showed up there. Later, it was measured right here on Earth, in a laboratory, sending light up a tower and catching the tiny reddening over just a few floors. Every version of the test agreed with the theory, and that third prediction, light reddening as it climbs out of gravity, points straight at the single most down-to-earth consequence of Einstein's whole theory, the one that affects nearly everyone alive without their ever knowing it. Gravity changes time, and there's a machine in orbit right now that would fall apart if the engineers pretended otherwise. Start with the plain fact, because it's genuinely hard to believe the first time. Time runs slower deep in gravity and faster up high. A clock on the floor runs slower than a clock on the ceiling, not because either clock is broken. Time itself is passing at different rates in the two spots. This is gravitational time dilation, and it's the same thing as the falling man and the slow clocks Einstein predicted from the very start back in 1907, before he even had the full theory. The reason nobody noticed it for all of human history is that on Earth the effect is fantastically small. The difference between floor and ceiling is measured in tiny slivers of a second, far too little for any ordinary clock to catch. To put a size on it, consider the whole age of the Earth, about 4.5 billion years. Over that entire span, the center of the Earth, sitting deepest in the planet's gravity, has aged about 2.5 years less than the surface. The core is younger than the crust by a couple of years, after 4.5 billion of them. Or take a clock at the top of a tall mountain, up where gravity is a hair weaker, and one at sea level. Over the age of the Earth, the mountain clock would run ahead of the sea level clock by only a day and a half or so. These are absurdly small gaps, which is exactly why it took an Einstein to suspect they were there at all. But small doesn't mean unreal, and once clocks got good enough, the effect showed up right on schedule. In 1959, two physicists named Pound and Rebka did it in a single building. They sent light up a tower a few dozen feet tall and measured at the top that its color had shifted by the tiny amount the theory predicted, because the light had climbed up out of gravity and lost a sliver of energy on the way. A few floors of a building was enough. Later, atomic clocks were flown around the world on airplanes and came back disagreeing with the clocks left on the ground by just the predicted amounts, part from their speed and part from their altitude. The effect has now been measured across height differences of less than the length of a person's arm. Raise a good enough clock by a foot, and it ticks very slightly faster than its twin on the table below. Time really is different at the head and the feet. The head, a little farther from the Earth's center, ages a hair faster than the feet. Over a lifetime, it comes to a few billionths of a second, but it's real and it's measured. Now for the machine. Overhead, day and night, a fleet of satellites is circling the Earth carrying atomic clocks, and they run the system that tells phones and cars and ships exactly where they are. It works by timing. Each satellite broadcasts the time from its onboard clock, and the receiver on the ground listens to several satellites at once and uses the tiny differences in when their signals arrive to work out its own position. The whole thing lives or dies on those clocks, agreeing to fantastic precision, because light and radio travel so fast that a timing error of even a millionth of a second throws the position off by the length of a football field or more. And here's the catch. Those satellites are in two of Einstein's situations at once. They're high up, far above the ground, where gravity is weaker, so their clocks run faster than clocks on the surface. And they're racing around the Earth at high speed, and by special relativity, fast motion runs clocks slow, so that pulls the other way. The two effects don't cancel. The altitude wins, and the net result is that a satellite clock ticks a little faster than a clock on the ground every single day by a definite, calculable amount. If the engineers ignored this, the timing would drift, and the position errors would pile up hour after hour, and within a single day, the whole system would be useless, telling people they were miles from where they actually stood. So the engineers don't ignore it. The clocks are deliberately built and adjusted to account for both of Einstein's effects before they ever go up. General relativity isn't a curiosity for the satellite navigation system. It's a correction that has to be dialed in for the thing to work at all. Every time a phone finds itself on a map, it's quietly using the fact that time runs at different speeds, at different heights, which a patent clerk worked out from a thought about a falling man more than 100 years ago. That's the everyday face of the theory, the humble one, running in the background of ordinary life. But the same rule that makes a mountaintop clock tick faster has a monstrous extreme hidden inside it. If a little gravity slows time a little, then a lot of gravity slows time a lot. And piling up enough gravity in one place slows time so much that it very nearly stops. Einstein wrote his equations in November of 1915 and assumed nobody would ever solve them exactly. 2 months later, a solution arrived in the mail from a soldier at the front, and buried inside it was a place where time comes to a halt. The soldier was Karl Schwarzschild, a German astronomer already well known before the war, who had volunteered for the army even though he was middle-aged and didn't have to. He was serving at the front, where among other duties he calculated the paths of artillery shells. Somehow, in the middle of a war, in those conditions, he got hold of Einstein's brand new papers on general relativity, and he sat down and solved the equations. Not approximately, exactly. He worked out the precise shape of space-time around a single round mass sitting all by itself. The very case Einstein had assumed was too hard to crack. He mailed his work to Einstein in the early weeks of 1916. Einstein was astonished. He wrote back that he hadn't expected anyone to find so clean a solution so quickly, and he presented Schwarzschild's result to the Academy in Berlin on his behalf. The paper was published in January of 1916, barely a month after Einstein's own. Schwarzschild didn't live to see where it led. At the front he came down with a rare and painful skin disease, and it killed him just a few months after his paper appeared. He solved the deepest equations in physics from a battlefield and was dead before the year was out. The same solution was found independently around the same time by a Dutch physicist named Johannes Drost, working in peace and quiet by a simpler route. But it carries Schwarzschild's name, and given how he came to it, that feels right. What his solution describes is the ordinary case, and that's what made it so useful. It gives the exact curved space-time outside any ball-shaped mass that isn't spinning and isn't electrically charged, which is a fine description of a planet or a star or the sun or the earth. Feed in the sun's mass, and Schwarzschild's solution gives exactly how space-time curves around it, and out of that come Mercury's orbit and the bending of starlight, the very things being tested. For any normal star or planet, the solution is well behaved and unremarkable. It's just Einstein's version of the gravity outside a round object. But the solution had a strange number sitting inside it, and it belongs to every mass, the sun's, the earth's, a person's. For any given lump of matter, there's a particular size called the Schwarzschild radius, and it marks a threshold. As long as the object is bigger than its Schwarzschild radius, and nearly everything in the universe is far, far bigger, nothing odd happens. The sun's Schwarzschild radius is only about 3 kilometers, less than 2 miles, while the actual sun is some 700,000 kilometers across. So the special radius sits deep inside the sun, in a region the solution doesn't even apply to, because there's solar matter there, not empty space. It's just a number, harmless, buried where it can't do anything. For a planet like the Earth, the Schwarzschild radius is smaller still, small enough to cup in 2 hands. Ordinarily, it means nothing. The question that unlocks everything is simple. What if all that mass could be crushed down smaller than its Schwarzschild radius? Squeeze the whole sun into a ball less than 2 miles across. Squeeze the whole Earth down to something small enough to hold in 2 hands. Now the special radius is out in the empty space around the crushed object, where the solution does apply, and now it does something. At that radius, Schwarzschild's math goes haywire. The time dilation, the slowing of clocks that gravity always causes, grows without limit close up to it. A clock lower toward that radius runs slower and slower, seen from far away, and right at the radius it appears to stop entirely. Light trying to climb out from there loses all its energy and fades to nothing. From outside, the surface at the Schwarzschild radius looks like a place where time freezes and light dies. For a long time, physicists, including Einstein, looked at that and assumed it was either a mathematical mistake or a sign that nature simply wouldn't allow such crushing to happen. They figured some pressure, some force, would always halt a collapse before an object shrank past its Schwarzschild radius, so the frozen surface would never actually form, and the weird math would never matter. And it took decades and a lot of argument to sort out what that surface really is. Part of the confusion was that the equations blow up there in a way that turned out to be a trick of the coordinates, like the way every line of longitude crowds together and the directions go crazy right at the North Pole, even though the pole is a perfectly ordinary patch of ice. Cross to a better way of describing it, and the frozen surface isn't a physical wall at all. Someone actually falling toward it would sail right through, feeling nothing special at the crossing, noticing no barrier. But sailing through is a one-way trip. That surface, the sphere at the Schwarzschild radius, is the event horizon, and it's the real subject of this whole part of the story. It's not a thing made of matter. It's a place in space-time, a boundary, and the boundary has a brutal property. Anything can cross it going in, and nothing can ever cross it coming back out. And there is one more thing hiding in Schwarzschild's solution, deeper in, at the very center, there at the middle. The curvature doesn't just misbehave, it truly runs to infinity, and space-time itself stops making sense. That center is a true singularity, and it's the thing physicists spent 40 years refusing to believe was real. The event horizon deserves a careful look on its own, because it's one of the strangest things in all of physics, and it's not made of anything. An event horizon is a boundary in space-time, beyond which no signal of any kind can ever reach an outside observer again. The name was coined in the 1950s by a physicist named Wolfgang Rindler. Everything inside the horizon is sealed off from everything outside, permanently in one direction. Light, radio, a shout, a last wave goodbye. Nothing that starts inside can ever get out. And the wall doing this sealing isn't a surface anything could touch. It's a line drawn in space-time itself, marking where the geometry has tilted past the point of no return. Here's what tilting past the point of no return means. Far from any mass, light can go any direction it likes, including straight up and away, out to the distant stars, yet closer to a very heavy, very compact object, and space-time curves, and the paths available to light start leaning inward. At the event horizon, the curving reaches a tipping point. Right there, light aimed straight outward, with everything it's got, exactly holds still, hovering, unable to gain a single inch of ground. And just inside the horizon, even light aimed straight out is carried inward, because every possible path now leads deeper in. This is the eerie heart of it. Inside the horizon, moving toward the center becomes as unavoidable as moving into next week. The center stops being a place in space that could be steered away from and becomes a moment in the future that cannot be dodged, the same way tomorrow keeps coming, no matter what anyone does. Rockets don't help. Pointing away from the center doesn't help. Every direction, physically, is toward the center because the future itself points that way. The idea, in a rough form, is surprisingly old. Back in 1784, an English clergyman and scientist named John Michell worked out, using Newton's gravity and the notion that light was made of little particles, that a star could in principle be so massive and compact that its escape speed would top the speed of light, so light couldn't get away and the star would be dark. He imagined dark stars a century and a half before anyone had the real theory. But the Newtonian version was a pale shadow of the truth. It pictured light as cannonballs slowing down, rising and falling back, which isn't what happens. The real event horizon, the one from general relativity, is about the shape of spacetime, and it's far stranger. The modern, proper definition came in 1958 when a physicist named David Finkelstein used Einstein's theory to describe the horizon as a one-way membrane, a surface that can be crossed in only one direction, letting things in and never back out. The cruelest part is how the horizon looks from the two sides, because the two views flatly disagree. Picture an astronaut falling toward the horizon while a friend watches from a safe distance far away. To the distant friend, the astronaut never actually reaches the horizon. As the astronaut falls, their image slows down because time down there is running slower and slower from the friend's point of view. The astronaut seems to creep toward the horizon and freeze just above it, hanging there forever, their light stretching redder and dimmer until it fades from sight. The friend never sees the crossing. To the friend, the astronaut is eternally frozen at the edge, a fading after image. But to the astronaut themselves, nothing of the sort happens. They fall smoothly toward the horizon and cross it in a perfectly ordinary amount of time, with no wall, no barrier, no flash, nothing to mark the most important boundary they will ever cross. For a big enough black hole, they might not even be able to tell. The moment they passed the point of no return, one instant escape was possible. The next instant it wasn't, and nothing local announced the change. The horizon is real, but it's a global fact about the whole space-time, not a thing anything bumps into. The astronaut only learns the truth later, when they try to turn back and find that there is no back to turn to. What lies beyond, waiting in the astronaut's unavoidable future, is the center, the true singularity, where Schwarzschild's math ran to infinity. There the tidal stretching of gravity grows without limit. Long before the center, the difference in pull between the astronaut's head and feet becomes savage, stretching them out into a thin strand, a fate physicists have named, with dark humor, being turned into spaghetti. For a small black hole, this stretching gets lethal even before the horizon. For a giant one, it stays weak at the crossing and only turns deadly deep inside. Either way, the ending is the same. Everything that falls in reaches the center in a finite time, and at the center space-time stops. What happens there, general relativity cannot say, because the theory breaks down at exactly that point. It predicts its own blind spot, an object crushed inside its own event horizon, wrapping a singularity in a one-way surface, has a name that took decades to catch on and now belongs to popular imagination: a black hole. For 40 years after Schwarzschild, most physicists, Einstein included, thought black holes were a mathematical fantasy, a place where the equations misbehaved, something nature would never actually build. They were wrong. The universe is full of them. Getting from a mathematical oddity to a real object Took another 40 years and a lot of stubborn resistance, and some of the loudest resistance came from the biggest names. Arthur Eddington, the same man whose eclipse expedition had made Einstein famous, publicly mocked the idea that a star could shrink down to its Schwarzschild radius, calling it a flaw in a theory that wasn't yet fully understood. And in 1939, Einstein himself wrote a paper trying to prove black holes were impossible. He argued that some pressure or some spinning would always rise up to halt a collapse before it went too far. He was wrong, and the reason is telling. He assumed the star would settle into a steady balance. He missed that a real collapse is violent, an implosion, and an implosion can blow right past the critical size before anything can stop it. The people who worked out what really happens were studying how stars die. A star holds itself up by burning fuel, and the outward push of that fierce heat balances the inward pull of its own gravity. But fuel runs out. A big star fuses lighter elements into heavier ones, working its way up the ladder until it reaches iron. Iron is the dead end, because fusing iron takes energy instead of releasing it. So once the core is iron, the fire goes out. With nothing pushing back, the core collapses under its own weight in an instant. What happens next depends on how much mass there is. In the 1930s, a young physicist named Subramanian Chandrasekhar showed that a modest dead star settles as a white dwarf, held up by a strange quantum stubbornness of its electrons, a pressure that comes from the fact that these particles simply refuse to be crowded into the same state. But that stubbornness has a limit. Above a certain mass, the electrons can't hold the line, and the star crushes further, down to a ball of neutrons, packed as tight as an atomic nucleus, a neutron star, a thing the size of a city, with more mass than the sun. And that has a limit too, around 2 times the mass of the sun. Push past it, and nothing known can stop the fall. Chandrasekhar's own mentor, Eddington, found the conclusion so distasteful that he insisted some unknown law must save the star. There was no such law. In that same year, 1939, while Einstein was arguing black holes couldn't form, 2 other physicists, Robert Oppenheimer and Hartland Snyder, did the honest calculation. They took Einstein's equations and let an idealized star collapse without anything to stop it, and they followed it all the way down. What they found is the modern picture of a black hole being born. Seen from far away, the collapsing star falls inward, faster and faster. But then, as it nears its Schwarzschild radius, the time dilation takes over. From the outside, the star seems to slow and stall and freeze just above where the horizon forms, its light stretching redder and dimmer until it fades from view. Seen from the surface of the star itself, though, there's no stalling at all. The collapse plunges straight through in a finite time, past the horizon, down to the center. A black hole forms, wrapped in its event horizon, hiding its singularity, exactly as Schwarzschild's math had hinted 23 years earlier. For a while the world wasn't ready to hear it, in part because of the war, in part because it was just too strange. But in the 1960s, everything changed. In a stretch of years people now call the golden age of black hole research, when the subject moved from the fringe into the heart of physics, new solutions were found, including the one for a spinning black hole, which is its own remarkable story. A deep result emerged that Wheeler summed up by saying a black hole has no hair, meaning that once it settles down, a black hole is one of the simplest objects in all of nature. It remembers only 3 things about everything that ever fell into it: its total mass, how fast it spins, and its electric charge. That's all. 2 black holes with the same mass, spin, and charge are identical, no matter whether one was built from stars and the other from dumped encyclopedias. Everything else, every detail of whatever fell in, is erased from the outside view, and a mathematician named Roger Penrose proved something that finally broke the old hope that the singularity was just an artifact of assuming perfect roundness. Penrose showed that once a collapse passes the point of no return, a singularity has to form, in general, messiness and all. Nature really does make these things. Penrose got a share of the Nobel Prize for that work more than 50 years later in 2020. Meanwhile, the term itself got its name. For years, these objects had clumsy labels like collapsed stars. Then, around 1967, at a lecture by John Wheeler, someone in the audience reportedly called out the phrase black hole, and Wheeler, who had a knack for a good name, adopted it on the spot. It stuck hard. The phrase seems to trace back a little earlier to another physicist comparing these objects to a notorious prison people entered and never came out of. Whatever the exact path, the world had its word, and the word did half the work of making people take the idea seriously. So what actually is out there in the sky right now? Black holes come in a few sizes. The common kind are the stellar black holes, the corpses of big stars, running from a few times the mass of the sun up to a few dozen. Then there are the monsters, the supermassive black holes, weighing millions or even billions of times the mass of the sun, and one of these sits at the center of nearly every large galaxy, including our own Milky Way. In between, there's a rarer middleweight class, and possibly left over from the birth of the universe, some tiny ones, though those have never been confirmed. The giant ones didn't come from single stars. They grew over billions of years, swallowing gas and stars, and merging with other black holes, feeding at the hearts of galaxies. And here's the thing that surprises people. For all their reputation as cosmic vacuum cleaners, black holes don't reach out and suck things in from afar. From a distance, a black hole's gravity is exactly the same as the gravity of any ordinary object with the same mass. If the sun were somehow swapped for a black hole of the same weight, the Earth wouldn't get pulled in. It would keep right on orbiting in the same orbit, just in the cold and dark, because the gravity out here wouldn't change one bit. A black hole is only dangerous up close, near its horizon. Far away, it's just another mass. The strangest twist is that these invisible objects, which by definition give off no light, produce some of the brightest fireworks in the entire universe. When gas falls toward a black hole, it doesn't drop straight in, it spirals, forming a flat, whirling disk. And in that disk, the gas rubs against itself, faster and faster, hotter and hotter, until, just before it crosses the horizon, it's glowing ferociously, blasting out X-rays across the galaxy. Some black holes fire out enormous jets of matter from their poles, beams shooting thousands of light years into space. The brilliant beacons called quasars, the brightest steady objects in the sky, visible clear across the universe, are supermassive black holes at the centers of young galaxies, blazing as they feed. The black hole itself is dark. The doomed matter falling into it lights up the heavens. That glow is how we find them, because the horizon itself gives off nothing. And the evidence, once the tools got good enough, became overwhelming. At the center of our own galaxy, astronomers spent decades tracking the motions of stars whipping around an invisible something. They watched over 100 stars orbit an unseen point, and one star, called S2, they followed all the way around a complete orbit. From how fast those stars move, the hidden object has to weigh about 4 million times the mass of the sun. all packed into a space smaller than our solar system. Nothing but a black hole can do that. The two astronomers who led that decades-long star tracking, Andrea Ghez and Reinhard Genzel, shared the other half of that same 2020 Nobel Prize with Penrose. And then, in 2019, people actually saw one. A network of radio telescopes scattered across the whole planet was linked together to act as a single telescope nearly the size of the Earth, sharp enough to make out something the size of a black hole's shadow in a distant galaxy. On the 10th of April, 2019, they released the first picture ever taken of a black hole, the giant one at the heart of a galaxy called Messier 87, tens of millions of light years away. It showed a bright ring of hot glowing gas wrapped around a round patch of pure darkness, the shadow of the event horizon, looking almost exactly as the equations of general relativity said it should. A few years later, the same team turned the trick on the black hole at the center of our own galaxy and imaged it too. The dark objects Einstein tried to prove impossible now sit in photographs. There's one last twist, and it comes from mixing general relativity with the physics of the very small. In the 1970s, Stephen Hawking showed that black holes are not perfectly black after all. Because of the strange rules of quantum physics, right at the edge of the horizon, a black hole should very slowly leak a faint trickle of radiation, and over unimaginable spans of time, it should shrink and eventually evaporate away entirely. The effect is fantastically weak for any real black hole. A black hole, the mass of the sun, would glow at a temperature of about 62 billionths of 1 degree above the coldest possible temperature, far colder than the faint warmth left over from the Big Bang that fills all of space. So real black holes today aren't shrinking, they're growing, soaking up more than they leak. But the idea opened a crack between general relativity and quantum physics that nobody has fully closed. A puzzle about whether the information that falls into a black hole is truly gone forever. That puzzle is still open. It's one of the places where Einstein's theory, for all its triumphs, admits it isn't the last word. That open puzzle sits at the far edge of the theory, where it runs into the physics of the very small, and no one has closed it yet. Back in the part of the world the theory handles cleanly, though, there was still more to say about black holes themselves. The one Schwarzschild found in the trenches was the simplest kind there is. It just sits there, round and still, doing nothing but pulling. Real black holes are almost never still. They spin, and most of them spin fast, because the stars they formed from were spinning, and that spin has nowhere to go. Working out what a spinning black hole does to the space around it turned out to be much harder than the still case. Schwarzschild had his answer within a couple of months of Einstein finishing the theory. The spinning answer took almost 50 years. It finally arrived in 1963 from a mathematician named Roy Kerr, and the shape he found is stranger than the plain black hole in every way that matters. A spinning mass doesn't only dent space-time, it drags it. Picture a heavy ball turning slowly in a jar of honey. The honey right against the ball gets pulled around, wound along in the direction of the spin. Space-time does the very same thing. Close to a spinning black hole, space itself is turning, coiled around the hole like water circling a drain. Anything that comes near gets carried along with the swirl. Nothing is pushing it. The floor of space is simply moving, and whatever stands on that floor moves too. This effect has a name, frame dragging, and it isn't only a black hole trick. Even the Earth turning slowly on its axis, drags the spacetime around it by the smallest amount. In 2011, a delicate satellite experiment called Gravity Probe B measured that tiny drag directly, and the numbers matched what the theory had promised. Around the spinning black hole, the dragging grows so strong that, past a certain line, holding still becomes flatly impossible. Inside that line, an astronaut firing their rockets as hard as they could, straining to stay in one spot, would still be swept around the hole. Space is moving faster than they could ever fight. That region has a name, the ergosphere, and it sits outside the point of no return, wrapped around it like a bulging shell. Something remarkable hides in there, because the ergosphere lies outside the true edge of the hole. A clever visitor can dip into it and climb back out, and if they throw something away at just the right moment while inside, letting the discarded piece fall down into the hole, they can climb out with more energy than they carried in. The extra energy comes straight out of the black hole's spin, bleeding it off, slowing the giant down by a hair. In principle, a spinning black hole is a battery. Its turning holds a vast store of energy, and there are honest ways to draw some of it out. The spinning solution has one more surprise waiting at its heart. The still black hole hides a single point at its center where everything is crushed to nothing, a place the math simply gives up on. The spinning one, if the equations are taken at face value, hides something else, a ring, a loop of crushed space-time, turning forever. And through the middle of that ring, the math seems to allow paths that lead somewhere very strange, which is where honest physicists tend to hold up their hands and admit the theory is being pushed past the point where anyone trusts it. What sits at the center of a real spinning black hole is one of those places where general relativity says something wild and no one is sure whether to believe it. For a long time, all of this was pen and paper. Kerr's spinning hole was a solution to an equation, a shape that lived in a notebook. Then, in 2016, a pair of detectors caught two black holes falling together and merging far out in space. And when the signal was studied, the spinning black holes in it fit Kerr's 50-year-old geometry. The notebook shape was real. That story is coming, because it's the best one the theory has. First, though, the theory has to grow all the way up, from single stars and single holes to the thing that holds all of them, the whole universe at once. This is the last and largest step. The same equations that bend light around a single star, that stop a clock at the edge of a single black hole, can be pointed at everything there is, all the matter and all the space in one go. When Einstein tried it in 1917, he got a shock. His own equations refused to sit still. A universe full of matter, all of it pulling on all the rest, could not simply hang there unchanging. It had to be either falling together or flying apart. That bothered him. Everyone at the time took for granted that the universe as a whole was fixed and eternal, the same today as always. So Einstein added a small extra term to his equations by hand, a kind of built-in push spread evenly through all of space, tuned just right to hold the universe still against its own gravity. He called it the cosmological constant. It was a patch, and he wasn't proud of it. While he was patching, other people were taking the raw equations at their word. A Russian named Alexander Friedman worked out in the early 1920s that Einstein's theory allowed a whole family of universes, and almost all of them were moving. They could expand, they could collapse. Their overall shape could be open and endless, or flat, or curved around and closed, like the surface of a ball. A few years later, a Belgian priest and physicist named Georges Lemaitre found much the same thing on his own, and he took the boldest step. If the universe is expanding now, he reasoned. Then it was smaller yesterday, and smaller still the day before, and running that backward far enough, everything there is was once packed together into a single dense speck. He called it the primeval atom. Later, people would call the whole idea the Big Bang, and the name was first thrown out as an insult by someone who thought it was ridiculous. The idea needed proof, and the proof came from the sky. Out at the telescopes, astronomers had been noticing something odd about the faint spiral smudges scattered across the dark. The light from almost every one of them was shifted toward the red end of the spectrum, stretched out, the exact fingerprint of something rushing away. In 1929, an American named Edwin Hubble pinned it down. He worked out the distances to those spirals and found they weren't smudges of gas inside our own galaxy at all. They were whole other galaxies, islands of billions of stars, unthinkably far away, and the farther one sat, the faster it was fleeing. Twice as distant meant twice the speed, in a clean, steady march. There's only one simple picture that does that. The whole of space is swelling, and every galaxy is riding along as it grows. So every galaxy sees all the others drifting away. Nothing sits at the center. The bread is rising, and the raisins are all spreading apart. The universe was expanding, exactly as the untouched equations had said it could. Einstein dropped his extra patch and, by the usual telling, called it the biggest mistake of his career. There was still a long fight over what the expansion meant. One camp took Lemaitre's road, a hot, dense beginning that had been thinning and cooling ever since. Another camp argued the universe had always looked more or less the way it does now, with fresh matter quietly appearing to fill the widening gaps. The two pictures ran neck and neck for years. Then, in 1965, two engineers at a radio antenna in New Jersey found a faint hiss coming from every direction in the sky, a whisper of microwaves they couldn't get rid of, no matter how they cleaned their gear. It turned out to be the oldest light there is, the afterglow of the whole universe, from when it was young and hot and first turned clear, stretched by all the eons of expansion down into a cold, even glow. That glow had been predicted by the hot beginning camp. Finding it all but ended the argument. The universe had a fiery start, and it has been expanding and cooling ever since, for something close to 14 billion years. The picture that came together from all this is built on the same equations Einstein wrote for gravity near a star, only now the source of gravity is everything, spread out smooth across the cosmos. It describes a universe that started in a hot, dense state, blew outward, cooled, and clumped up under gravity into stars and galaxies and the great cobweb structure of clusters and voids we see around us. And it works. It predicts how much of the lightest elements should have been cooked up in the first few minutes, and the measured amounts agree. It predicts the pattern of that cold afterglow down to fine detail, and the satellites that mapped the sky found exactly that pattern. The honest part of the story is that the picture only works if most of the universe is made of things no one has ever touched. To make the galaxies spin the way they do, and to bend light the way they do, there has to be far more matter out there than everything that glows. That unseen stuff is called dark matter, and its nature is still an open question. And there's a second, stranger piece. Near the end of the 20th century, astronomers measuring very distant explosions expected to see the expansion slowing down, dragged on the brakes by all that gravity. They found the opposite. The expansion is speeding up. Something is pushing space apart faster and faster, and no one knows what it is. so it goes by the name dark energy. The odd thing is that it behaves almost exactly like that extra term Einstein once added to hold the universe still and then threw away in embarrassment. His patch, or something very like it, seems to be real, after all, doing the reverse of what he wanted. Between the dark matter and the dark energy, the ordinary stuff of stars and planets and people turns out to be a thin skin on top of a universe made mostly of two things nobody understands. There's one prediction left, and it's the one the whole theory had been promising from the start. If gravity is the bending of spacetime, and if a moving mass changes the way spacetime is bent, then a mass that shakes hard enough should send that change rippling outward, a wave of bending spreading through space itself at the speed of light. Einstein saw this in his own equations back in 1916. He called them gravitational waves, and almost at once he doubted them. The effect they'd have on anything measurable was so absurdly small that he wasn't sure they'd ever be more than a line of math. At one low point, nearly 20 years later, he even talked himself into believing they couldn't exist at all, and wrote a paper saying so, before a careful reviewer caught the error, and he quietly turned the paper around. For most of a century, the waves stayed exactly what he'd feared, a prediction on paper that no one could check. The trouble is how faint they are. A gravitational wave stretches and squeezes everything it passes through, space itself, and the rulers along with it. But the stretch, by the time a wave reaches us from anything far enough away to matter, is smaller than small. A strong one, born in the most violent event in the sky, might change the length of a thing by less than a thousandth of the width of a single proton. Measuring that is like measuring the distance to the nearest star and catching a change the width of a human hair. For decades it looked hopeless. The first hint that the waves were real came sideways, without anyone catching a wave at all. In 1974, two astronomers found a pair of dead stars whirling around each other far off in the galaxy. One of them a pulsar, a spinning beacon so regular it worked like a perfect clock. Over years of watching, that clock showed the two stars slowly spiraling inward, losing energy, drawing closer at a steady creep, and the rate they lost energy matched exactly the amount general relativity said should be leaking away as gravitational waves. No one saw the waves, but the orbit was paying for them, right on schedule. That was enough to earn a Nobel Prize, and enough to convince almost everyone the waves were out there, waiting. Catching one directly took a machine of almost unreasonable ambition. It's called LIGO, and it's really two machines, one in Louisiana and one in Washington state, most of a continent apart. Each is a giant Lel lying on the ground, with two arms reaching out 4 kilometers in different directions. A laser beam runs down each arm, bounces off a mirror at the far end, and races back, and the two beams are compared against each other with fantastic care. If a gravitational wave rolls through, it stretches one arm and squeezes the other by the tiniest sliver, and the returning beams fall out of step by just enough to notice. Two machines were built instead of one for a simple reason. A passing truck or a small earthquake could jiggle one of them. A real wave from space would sweep across both, catching them almost together, and only signals that showed up in both would be trusted. On the 14th of September, 2015, early in the morning, both machines twitched. The same faint pattern ran through the detector in Louisiana, and then, 7 thousandths of a second later, through the one in Washington, the gap being just the time a wave moving at light speed needs to cross from one to the other. When the scientists unfolded what they'd caught, the story in it was staggering. More than a billion years ago, and more than a billion light years away, two black holes had been locked in a death spiral, whirling around each other faster and faster, one about 29 times the mass of the sun, the other about 36. In their final moment, they slammed together and merged into a single black hole around 62 times the sun's mass. Add the two starting masses, and the total tops 65. The merged hole was 62. The missing 3 suns worth of mass had been turned in a fraction of a second into pure energy, poured out as a scream of gravitational waves. For that instant, that one collision radiated more power than every star in the whole visible universe put together. Almost none of it came out as light. It came out as the shaking of space, and after traveling for more than a billion years across the cosmos, a whisper of that shaking passed through the earth, through the detectors, through everyone standing in the room, and moved two mirrors by less than the width of a proton. They announced it to the world on the 11th of February, 2016. It landed almost exactly 100 years after Einstein had written the papers that predicted it. The papers whose own author doubted this day could ever come. The prize followed the next year for the three men most responsible for building the impossible machine. And the black holes in that first signal, when their spins were read out of the waveform, matched the spinning geometry Roy Kerr had found with nothing but a pencil half a century before. Two of his notebook shapes, real all along, had collided out in the dark and rung space-time like a bell. It hasn't stopped since. A couple of years later, the detectors caught two neutron stars colliding, and this time telescopes swung around and saw the flash of light from the same event, waves and light arriving together, two utterly different messengers from one crash. What began as a single stubborn idea about a falling man has become a new way of listening to the universe, one that hears the collisions of black holes a billion light years off. Every year now, the detectors catch more of these collisions. Two more machines join the hunt, one in Italy and one buried under a mountain in Japan, and together they've logged black holes and dead stars falling into each other all across the sky, dozens of them, then hundreds. Each catch is another test the theory has to pass, and it keeps passing down to the fine shape of every wave. There's something worth sitting with in what these machines really are. For 400 years, almost everything the human race learned about the sky arrived as light. Sometimes it was light the eye could see, and sometimes it was the invisible cousins of light, the radio waves, and the infrared and the X-rays, and it was all the same kind of thing. Every telescope ever built was, in the end, a sharper eye. Gravitational waves are a different messenger altogether. They're closer to a sound than a sight, a shudder running through the fabric of space rather than a beam crossing it, and space barely touches them. Light gets scattered and soaked up by dust and gas, so there are ages and corners of the universe the eye simply cannot reach. A gravitational wave slides through all of it, through clouds and stars and whole galaxies, and arrives a billion years later carrying almost the same shape it left with. A theory that began with one man shutting his eyes and picturing a fall had, a century on, handed people a brand new sense, an ear laid against the universe, and the first thing that ear heard was two black holes, a billion years gone, ringing space-time like a struck bell. So here is the whole arc, from the beginning. A man imagined himself falling, and felt his weight vanish, and understood in that instant that gravity and acceleration are the same thing, wearing two faces. From that one thought he built, over 10 hard years and more than a few wrong turns, a theory that threw away the idea of gravity as a force and replaced it with the shape of space and time. The theory said mass bends space-time, and things moving through the bends trace out the paths we call falling. It said clocks run slow near heavy things, and the satellites overhead have to correct for it, or they'd lead us astray. It said light would bend around the sun, and it did, watched during an eclipse. It said there could be places where space-time folds up so hard that nothing escapes, and we've now taken their picture. It said the whole universe must move, and it's expanding, and it said space itself can ripple, a possibility its own author was half sure would never be seen. On a September morning, 100 years on, two machines felt that ripple pass, exactly the way the equations had always said it would. The falling man had been right about all of it, right about things he never dreamed anyone could check.